Chord. Oh well. They'll just have to deal without the other pieces. Okay, so 194. This problem is a corollary of triangle proportionality. Theorem. Corollary, in case you've forgotten, means this is a direct result of a theorem. It's not as big as a theorem in terms of like how new it is. It derives directly from a theorem. So the triangle proportionality theorem says, hey, if you have parallel lines in a triangle, these segments are going to be proportional to each other. Well, the same thing happens down here. We have parallel lines, so that means these segments will be proportional to each other. Okay. So that being said, we can now say that EF divides FG the same way that AB divides BC. We just set up a proportion. So let's see here. We know that EF is 4x plus 8, and FG is 5x minus 6. So I could say that 4x plus 8 divides 5x minus 6. And now we need the other side. So this is how we would write it as a proportion. Now, here's the part that seems strange to us. They didn't give us any values for AB and BC, but what did they tell us about those two things? They're equal to each other, right? They're marked as tick marks, mean they're congruent, right? So that means it doesn't matter how long they are. When I simplify this as a fraction, what does it simplify to? 1 over 1, right? You can put anything in here you want, right? If it doesn't matter, this could be 10 and 10. This could be z over z. Anything I put here is going to simplify down to 1 over 1, which means that's my proportion right there, because they're congruent. So we end up with 4x plus 8 is equal to 5x minus 6. That makes sense, because if these two guys are equal, that would mean that these two guys are equal because they're proportional to each other, right? So now we can solve. We get x equals 14. And I guess that's all they wanted. Just wanted to know what x was. Not too bad. So when you see those parallel lines, sets of 3 parallel lines like that, you go, oh, I have proportional pieces in there I can set up. All right. Jump over to number 201. All right. Tell me what you notice about these triangles. What do you got? Suggestions? They're proportional? Why are they proportional? They have congruent angles, 2 congruent angles, so by angle, they are similar triangles, and similar triangles have proportional sides. Okay, so Cynthia got to the end at the very start. We needed to work our way to it, though. So she was correct. Very nice work, folks. Thank you. Okay, so we have similar triangles, we have proportional sides. Now we just got to set up our proportion. Help me set it up, please. We have BD is 2x and CE is 7x plus 8. So what's my proportion going to be? Suggestions? I'm taking any suggestions. We'll look it over later. It could be wrong. I'm okay with that. 2 over 2x equals 9 over 7x plus 8. Okay, guys, have a look at that. See if you think that's going to work. So you were saying do 2x over 2 equals 7x plus 8 over 9?
Yes.
Totally fine. That would be the same as this. My question is this a good proportion? Are you guys okay with this proportion?
Yes.
Okay, it's comparing things in the right direction and correspondingly. Okay, so this is a good proportion. And Mr. Living asks a very valuable question, not just for my class, but for any algebra course. And that says if you have proportions, their inverses are equal to each other as well. That's always true. That's true for numbers as well. And you see that all the time. If you don't believe me, check this out. 2/3, that's the same as 4/6, right? Same thing? Flip them both around, what do you get? Same thing, right? So if you don't like having something on the bottom like this, feel free to do that inversion. That's a really nice trick, and it'll serve you well in algebra too. All right, so we're ready to cross and multiply, I guess. 18x 14x plus 16. And then I'll subtract the 14x. So we get 4x equals 16, so x must equal 4. Is that the answer?
Yeah.
Okay. Okay. Which answer choice? C and D. You only get to choose one. I guess we need to do some more work, don't we? Yep, got to do a little more work. This is part of the answer, it's just not the whole thing, right? Okay, so plug it back in, I guess. What's BD going to be? WD then. Cool. And that's sufficient. All right. Page turn.
Yeah, sorry, that's two.
All right, so we are up to 202. No, we don't need to do 202. You can do 202 without me, I think. Let's do 205. 205 is something different. And somebody had a question about 209. I'll do 213. There we go. I'm doing 3 problems. That's fair. It's about half. Okay, so first 205. It says determine whether these lines are parallel, perpendicular, or neither. Well, how can we do that? Suggestions? Slopes. Yeah? Do you need me to do this with you or no? Your call. Then do it for me. What's the slope? Show me how to do the slope in your heads, if you would. What's the slope for WX? What's the Y value going to be? How far did you move in the Y? 1 in the Y, and how much in the X? 1 over 3. Okay, so that's WX. That's the slope of WX. Okay, and what about the other one? Slope of YZ?
4 and negative 9.
Okay, positive 4 and positive 9? Yeah. Now, some people are wondering why this isn't a negative 4. Going from negative 6 to a negative 2. They feel not bad. And for me, guys, I don't know about you, but for me, whenever they ask me to find distances between numbers, I kid you not, in my head, a number line like pops up. I go, oh, negative 6 is over here. Negative 2 is over here. I'm going in a positive direction. So it must be a positive 4. That saves me from having to go negative 2 minus a negative 6 is that, adding the 6 and the, that's just too much work. Right? Going, here's negative 6, here's negative 2. I've obviously moved 4 units that way. Right? It's very, very intuitive. Right? So those are your answers. What does that mean? Is it parallel, perpendicular, or neither? Neither. Because parallel would be the same, perpendicular would be opposite reciprocal. Right? It would be switched in negative. Not even negative, right? Although if you look at those numbers, are they close? What do you think? Yeah, because 3/9 is a third, right? So this, if you graph these two things and you try using the graph as your basis, your eye might get thrown off, right? You'd be like, it looks like they might be parallel. So you need to actually look at the numbers to verify this. The numbers help us, whereas the picture may not. Okay, 209. We have carpenters. They use parallel wall studs to build support for walls. I can verify that's true. Carpenter has built 2 wall studs given by HG and CD. So if they're parallel, okay, we know some things about parallel lines being cut by transversals. We get congruent angles that are corresponding. We get all interior angles. We get same side interior angles that add up to 180. Okay, so keeping that all in mind, it says find the measure of BDC. BDC. They want us to find this angle right here. Well, let's see what we can do. If this is 98 degrees, guys, how much is this angle right here? Well, actually, let's just look right here. Look at this right here. Look at these parallel lines right there. Okay with that? Look at this transversal. These are same side interior. I'm basically ignoring that middle line. We don't need to worry about it. These are same side interior. Are they congruent or do they add up to 180? Yeah, one's obtuse, one's acute. They better not be congruent. So we can say that 180 minus 98, that's going to give us the angle we need. So that's I think that's 82 degrees. Okay. Difficult? No. Some people wanted to use all the other sides. That's totally fine if you do. If you do, you can say that 98, that's corresponds to it. This angle right here corresponds. This would also be 98 degrees. Right? So these two would be same side interior as well. If you didn't want to do that, you can say, well, I know that if I find this angle here, these are congruent because they correspond, and these two angles are a linear pair, so they have to add up to 180. So if I find that this is 82, so is that. There's a whole slew of ways to get the right answer here. Okay, no one way is the only right way.
So that would be like a short, like a
It could be. You could do it that way, sure. We ready to jump down to 213? You ready? Oh, you're on. We're ready to leave, Mr. Duncan. We're done. We're done for the day. Not quite. Okay, we'll move on, folks. Okay, so we have two sides of a triangle that are 3 and 6 feet long. Okay, and we need to find the third side. And this third side, guys, we want a range of values for it. So if we do 6 and then 3, if that was like if those two legs were sitting right on top of each other, what would have to be bare minimum? Bare minimum in order to make a triangle. Bigger than 3. So 4 would be a number. We need a range, so it has to be greater than something. It has to be greater than 3. So 4 would be a value. We know it has to be greater than 3. That's the first part. So we have the minimum. It has to be bigger than 3. Anything bigger than 3 is good. So B has to be greater than 3. That's true. Now the other extreme, 6, and then I make the 3 go out this way. If it was flat, if those were flat, what would have to be less than? Has to be less than. What's the maximum it has to be less than? So what value would work for our third side length? I'm hearing 9. So B has to be less than 9. If it was equal to 9, it would be flat as a pancake, wouldn't it? Yeah. And if it was longer than 9, then it wouldn't even make a triangle. You get that T-Rex syndrome, right? Can't quite touch, right? The hands can't touch.
Can't be greater than 9.
It has to be less than then. Yep. So B has to be less than 9. Now, usually they want you to write that as one statement, not two, like I've broken it up as. Yes, so here's how I recommend you write it. It makes so much more sense to me. Start with where B is. B's in the middle, right? You say, B must be greater than 3, but less than 9. So I said B must be greater than 3, but less than 9. So I didn't write this right to left. It didn't make sense to me to say it out loud that way. I spoke from the point of view of what values B could be. I said B has to be greater than this thing, but less than that thing. That makes sense. Right? It makes more sense. Saying out loud 3 is less than B is less than 9, that's mathematically true, but logically it doesn't make it's not intuitive, right? All right, page turn, home stretch, almost there. We're going to make it. All right, I don't think you need me to go over slope with you. If you do, come talk with me. I want to do fractional distance. This is the one I'm going to do with you. This is our last one. Okay. Now, fractional distance, it's the same exact thing as dilations, guys. It feels the same way. It's the same method. All we need to do is find out our original vector, scale it up or down, and then move that amount from our starting point. That's everything. So I want to find y such that it breaks up this line segment into a ratio of 2 to 3. First thing, touch up my problem. It needs to be touched up a bit. That should be z, and this should be x. So there's some typos. Just some quick typos. Fix them, please. So here's what I know. I need to find a value y such that it breaks up this line into 2 parts. 3 parts and 2 parts. That's a total of how many parts?
Say it again. 2 and 3.
3 parts and 2 parts. How many parts is that total? 5 parts. So I want to break this thing up into 5 parts. If I'm starting at z, how many of those parts do I need to go up? 3 or 2? Look at this. Look at this.
2.
Careful. From x down it would be 2. I'm going from z. So from z it's 3. Right? YZ compares to the 3. So it needs to be 3/5 from starting at z. Now, what I need is my vector that takes me from z up to x. What's the vector that gets from z over and up to x?
7.
7 over?
7 over and 7 over.
7 up. Oh, it's a good drink. Okay. So I'm now going to scale that vector down by a ratio of 3/5. Because I don't need to go the full 7 up and 7 over.
So 3/5 of 7.
So that gives me, what, 4.2, I think? So that's how far I need to travel. Where's my starting point, folks? X or Z? Z, because we started here, that means my vector is positive. Okay, so I'm going to add to this -1, 0. Can you see it looks exactly the same as when we did dilations? Exactly the same. This would be the center of dilation, basically. So I end up with my new coordinate at 3.2, comma, 4.2. That is the location of Y. And you have finished. That's it. B is doing the same problem, but now instead of a ratio of 2 to 3, it's a ratio of. So now you're using a different fraction, but the same vector. It's the same problem, basically, right? All right, gang, you have the rest of the problems to finish. Okay, check your email for those reviews, and I will be sending out the key for the problems you've already worked. By the way, your homework, you only get 1 day turnaround. Sorry, it's because you're Thursday. Tomorrow we're going to be checking these problems. You got to do them tonight. Okay? Gotta be.
Have a good day, Mrs.
Thank you, Deanne. You too. See you later.